Okay students, now I want to show you what happens when we apply a voltage source to the inverting input of an op-amp and the non-inverting input at the same time. So suppose we have an orientation like this. I have an input resistor and I'll label this V1, and then if I have another input resistor here and I label this V2, I'm going to tie both of these to ground. I have a terminal out here, and across this I'm going to measure my V out. Now, like other op-amp circuits, I'm going to have a negative feedback loop. So the resistor going through that loop, I'll label that RF. I'm also going to have a resistor that connects this non-inverting input to ground. So I'll label that R3, where this is R1 and R2. Okay, so we need to do circuit analysis on this to determine a relationship for V out in terms of my two V ins here. So I've got V1 and V2 are going to be my V ins. So in order to do that, I need to first label all my currents. So I have a current 1 that originates from V1, goes into this node. Some of it's going to split in this way. I'll label that IA. And some of it's going to come up here and take the path through the feedback loop. I'll label that IF. And then we've got a current that originates from V2, I'll call that I2. Some of it's going to come down here and take the path through the R3 resistor, I'll call that I3. And some of it will come into the op-amp like this, I'll label that IB, where this is my A input and this is my B input. So then I can label this node here my VA node, and this is my VB node. Okay, great. So now I'm ready for circuit analysis. First, at node VA, so this top node right here, by KCL, the current equations that I have are I1 comes into the node, and IA and IF go out. But by the ideal op-amp approximations, I know that IA is equal to IB is equal to 0. So this thing is actually going to be 0, and I'm just left with I1 is equal to IF. Now what I get to do is I'm going to replace my current equations with an equation in terms of V and R using Ohm's law. So that's going to be V1 minus VA divided by the resistor between. So I'm going to replace I1 with V1 minus VA over R1. And that's equal to IF. So to replace the IF current, that's going to be VA minus V out divided by the resistor between. So this is VA minus V out over the feedback resistor. Okay, great. So now what I want to do is I want to take this equation and I want to solve for V out in terms of V in. So let me bring this RF to the other side. This is RF over R1 times V1 minus VA is equal to VA minus V out. And I'm trying to get V out by itself. So this means that V out is equal to VA minus RF over R1 times the quantity V1 minus VA. So this means that VA minus RF over R1 times V1 plus RF over R1 times VA. So if I factor out my VA, this gives me the quantity 1 plus RF over R1 minus RF over R1 times V1. And this is my expression for V out in terms of V in from my first nodal analysis. So now let's let this sit tight for a second, and let's turn our attention now to node VB. So then at node VB, by KCL, we have that I2 comes into the node, I3 and IB come out. So this equation is going to be I2 is equal to I3 plus IB. But then by the ideal op-amp approximations, just like we did over here, we have that IA is equal to IB is equal to 0. So this thing goes to 0, and I'm just left with I2 is equal to I3. Now at this point, I can replace these currents with an equation in terms of V and R. So I2 is here. I'm going to replace that with V2 minus VB divided by the resistor between. So this is V2 minus VB over R2. And then I3 I can replace with VB minus 0, because this is my ground node, divided by the resistor between R3. So this is VB minus 0 divided by R3. And now what I want to do here, the goal is I want to get an expression for VB in terms of V2. And the reason why is because I am using the ideal Opamp approximation model, I know that VB is equal to VA. So if I can isolate VB over here, I can plug it into VA over here, and then I'll have an equation not in terms of VA and VB, but in terms of V1 and V2, which are my input source voltages. All right, great, so let's do that. This is going to give me, if I cross multiply, R3 times V2 minus VB is equal to R2 times VB, and my left-hand side is R3 V2 minus R3 VB. My right-hand side is still R2 VB. So I'm going to bring my my VB term over here. So this gives me R2 VB plus R3 VB is equal to R3 V2. I just switched places there. And we get VB times the quantity, R2 plus R3 is equal to R3 times V2. So now my expression for VB is going to be R3 over R2 plus R3 times V2. Now, as you can see, this is a scaling of V2 by this ratio of resistors. So what I want to do now is I want to take this VB that I just solved for, and I want to substitute that in for VA, because by the ideal Opamp approximation model, we have that VA is equal to VB. So let me go ahead and make this substitution, and I'm left with V out is going to be R3 over R2 plus R3 times 1 plus RF over R1 times V2. And then I still have this minus RF over R1 times V1. So take a look at this equation. This means that if I have two input source voltages, they can have weights depending on what my resistance values are in the circuit, and then I can subtract them to get my V out if I have a circuit orientation like this. Now you have to be a little bit careful because this is not a general formula for every difference amplifier. This is just for this particular orientation of the difference amplifier. So when you guys go to do these homework problems, you first recognize what kind of amplifier it is. We know this is a difference amplifier because we have an input voltage going to both the inverting and the non-inverting. And then you'll do circuit analysis just like we did here to come up with some relationship of resistors. So if you can put it in a form like this where you have V out as in terms of V1 and V2, then kind of put your resistance values all together in ratio form like this as coefficients. And then you can do like coefficient matching. So the coefficient in front of the V2 source is given by all these resistors. The coefficient in front of the V1 source is given by just RF over R1. So let me show you an example of what I mean by that. So suppose we are asked to design a difference amplifier. So we know that an orientation like this will work, so we can just do this, and we have already derived this equation. So maybe we're asked to design a difference amplifier such that V out is equal to -3 times V1 minus V2. Okay, so we need to pick the resistance values that will ensure that we get the correct weighting of V1 and V2 before they are subtracted. Okay, great. So what is this equation actually saying? This is -3 V1 plus 3 V2. So V2 is going to have a coefficient of +3, and V1 is going to have a coefficient of -3. So if I match this to my V out equation here, that means that if this is my V1 term and that's my V1 term in the equation, then I want RF over R1 to be equal to 3. See, this has a negative and this has the negative, so I don't have to worry about the negative. So we want RF over R1 to be equal to 3. So that means we can pick RF to be like 3K ohms, and we can pick R1 to be 1K ohms, and that will satisfy this first coefficient matching. Okay, so if we do that, then the coefficient of our V2 term is given by all this stuff here. So the coefficient from the V2 we want also to be 3. So that means we want R3 over R2 plus R3 times the quantity 1 plus RF over R1 to be equal to 3. But we've already designated RF and R1 as 3K and 1K. So this thing right here, we've already said that this ratio is 3. So this equation becomes R3 over R2 plus R3 times 1 plus 3 is equal to 3. So we want R3 over R2 plus R3 to be equal to 3 over 4, if I bring this guy over here. So what would be a good choice that would work? Well, we can let R3 be 3K ohms, and then we can let R2 be 1K ohms, and that would satisfy this requirement. So if I'm asked to make a difference amplifier that satisfies this equation for V out, I can pick these resistance values and put them into a circuit like this, and I will have satisfied the constraints. So let me know if you have questions about the difference amplifier, and we'll also talk about an averaging amplifier in the next video.